Hey, we're live. And just for giggles, I'm going to wander around for this lesson, just because. The least common multiple, continuing where we left off, of two or more numbers is the smallest, number that's divisible by each number. Say what? Well, what are the multiples of 6? What are numbers that 6 goes into evenly? I'll give you a hint. The first one is 6. What else does 6 go into evenly? What's the next one? 12, you say? Then? 18. And you can either multiply or add your way along this list. I'm actually just adding 6 in my head. So I know that 18 plus 6 is 24. Then I get 30. Then I get 36. Then I get 42, 48. And it goes forever. Those are multiples of 6. There's an infinite number of them. Oh, multiples of 8. Well, what's the first one? 8, 16, 24, 32, 40, 48, 56, 64, and it keeps going. I'll even put ... at the end of each of those to remind myself that it goes forever. A common multiple is a number that appears in both of those lists. The least common multiple is the smallest number that appears in both of those lists. What's the smallest number that appears in both of those lists? 24. By the way, common multiples are 24, 48. There's an infinite number of common multiples, but the least common multiple is 24. And Brandon, just like GCF, for smaller numbers, most of you can find the least common multiple intuitively in your head, sort of. So if I said to you, hey, what's the least common multiple of 6 and 5? What's the smallest number both of those go into? 30. What's the least common multiple of 448 and 652? Okay, maybe there's a procedure that we can get there without guessing and checking like crazy. What's the least common multiple of 5 and 7? 35. How'd you find that? 5 times, multiplying the numbers together will always give you a common multiple. It won't always be the least common multiple, but it's a good start. What's the least common multiple of 10, 15, and 20? 5 is the GCF, and yeah, kids get these two mixed up. Make sure you keep them straight. GCF, greatest common factor goes into it. Least common multiple, multiply, be thinking bigger numbers. Sorry? 60? Is he right? Now, if I was doing this in a guess and check method, I would say 60. I would probably try dividing by 2 just to check. Does 30 work? No. Then I would probably say, I think you're right. What about 15? 40 and 100. Yeah.
200.
Pardon me? 200? So his first guess is 200. Does 15 go into 200? I don't think so. Double check me. Don't write this down. I don't think that works. No. This one tight. Good thing I turned to my left. Okay, 200, no. Next. 300? Let's see. Does 40 go into 300? No? Now, we're clever enough to notice that since 100 has to work, it's got to end in 2 zeros. So I'm not going to try like 450 or 675. That'd be silly. So I'm looking, 300, 400, 500, hey, where does it work? Anyone? Yeah.
600.
Does 600 work? It does? It does. Now, Cole, what if I said to you, prove it? That's what we're going to look at. Because you'll notice this one took us some guessing. Probably still faster, Sarah, to guess our way to this particular answer here. But hey, what if the numbers were bigger yet? Or what is the procedure that can get us the least common multiple? And believe it or not, once again, it involves the prime factorization. So, in the above examples, it was fairly simple to find the LCM for parts A and B, but a little more complicated for part C. We need a method. There is one. You can use the prime factorization as your starting point. So if I wanted to find the the least common multiple of 15 and 40 and 100, or, Cole, if I wanted to prove that you were right, I would write the prime factorization of 15. 15 is what times what? 3 times 5. Forty is what times what? Pardon me? 20, those aren't prime. You know what? I'm going to cheat. I'm going to go over here really quickly. I'm going to go, you said 20 times 2. 2 is prime. We can break 20 down further, though. 20 is what? 10 and 2? 10 can go further. 10 is what? So 40 is 2 cubed times 5. Yes? What about 100? Hey, let's try and do this in our head. I know that 100 is what times what? It's 10 times 10. What's a 10? What times what? See, I think 100 is 2 times 5 times 2 times 5. In fact, I think it's, and I'm going to go smallest number. Oh, and now I see another way to think of 100 is 4 times 25. Yeah, it works. Mac, on a test or a quiz, I would do the full factor tree. I'm trying to see if I can push you to try and do some of this in your head so you can save time in the homework. All right? See our list? Okay. Here's how you can find the least common multiple. Does a 2 appear anywhere in those 3 lists? What's the biggest exponent on the 2 that appears? That's going to be part of my LCM. Does a 3 appear anywhere in that list? What's the biggest exponent of 3 that appears? It's a trick question, but yeah. I'll even put the 1 there just this once. Does a 5 appear anywhere? Yep. What's the biggest exponent of 5 that appears? I dare you to multiply those together. What do you get? Don't all rush for your calculators at once or anything. What?
600.
The answer that we got by guessing and checking and arguing and guessing and checking and arguing, we get 600? So there's a systematic way, Carl, to find the greatest common factor. And it is, do the prime factorizations of each number, and then for everything that appears, every number that appears, take the highest exponent on that number that appears, and that's going to show up in your product. By the way, this is wrong. I think I accidentally, when I was cutting and pasting this lesson together, copied the GCF rule, not the LCM rule. Sorry. It's not multiply the common factors and any additional factors. It's, hey, do you have a 2? Yeah. What's the biggest number of 2s you need? 3 of them. Does a 3 show up anywhere? Yeah. What's the biggest number of 3s you need? 1 of them. Does a 5 show up anywhere? Yeah. What's the biggest number you need? You need 2 of them. So let's use the prime factorization method to determine the least common multiple of 15 and 35. Okay. 15 is equal to what? What's the prime factorization of 15? 3 and 5. 35, what's the prime factorization of 35? The least common multiple, it's going to be, and this is why I always go from smallest to biggest. It makes it easier for me to keep track. Is there a 2 that appears in anything? Don't need to worry about that. Is there a 3 that appears in anything? Yeah, there is. What's the smallest exponent of the 3 that appears anywhere in that prime factorization? I'm going to need 1 3. Is there a 5 that appears in anything? What's the smallest number of 5s that I need? What's the smallest exponent that shows up? I need a 5. Is there a 7 that appears in everything? Sorry, not in everything. In anything. Doesn't have to appear in both. In anything. Yes? Have we covered everything? It's going to be 15 times 7, 15, 105? 105. And I know I'm right. Okay. Hey, try finding the least common multiple of 126 and 441 on your own. Now, this is going to be harder to do the prime factorization. You may want to use a factor tree or your calculator or something. I'll do it up here. Let's see if we end up in the same spot. $441. Wow. What goes into 441? 3 does, and it's going to go. I think that many times. 3 does again. It's going to go. Do this in my head. 7 squared is 49 times 2 is 98 times 9. 98 times 10 would be 980, so 98 times 9 is going to be 980 minus 98. It's going to be 900 minus 18 is going to be 882. I did it all in my head, so there's an entire chance I may be wrong. What? I'm right? Ooh. Sit up straight, Mr. Divick. I listed the GCF Kenzie of the, the prime factorization of the first 126, which turned out to be 2 times 3 squared times 7. I listed the prime factorization of 441, which turned out to be, why do you think I'm sitting in the back row, mister? Put the phone away. Which turned out to be 3 squared times 7 squared. Then I said, okay, how many 2's do I need? 1. How many 3's do I need? 2. How many 7's do I need? 2. So it's going to be 2 times 3 squared times 7 squared, 882. And you're saying I can get rid of the question mark? And I would argue if I'd asked you to guess your way to the 882, that would have taken longer than the systematic way. This is about where the systematic way is worth doing. Stuff this big. So Jacob, I don't care how you get the least common multiple. I just want you to get it. Some of you who are better at your times tables may be able to get there with the guess and check method. Hayden, pretty good. Oh, great. C. 22, 50, 154, and 190. Okay. 22, I think I can do the prime factorization of that in my head without showing any work. 22 is what times what? That's 2 times 11. 154. Okay. You ready? Instead of a factor tree, let's see if I can cheat and use my calculator. 154 divided by 2. What's left? Ooh, 77. I can do that one in my head. 77 is what times what? What's the prime factorization of 77? And I'm pretty sure 154 is going to be 2 times 7 times 11. And 198 divided by 2. Oh, 99. 99 is what times what? Is 9 prime? No, but I can write 9 as a prime. What's 9? 3 squared? I think this is going to be 2 times 9 times 11. The least common multiple is... Have I got a 2 showing up anywhere? Yeah. How many 2s am I going to need? 1. Have I got a 3 showing up anywhere? Yep. How many 3s am I going to need? Well, there's a 3 squared, so I'm going to need at least 2. I'm going to need 2. Is there a 5 in anything? Nope. Oh. Rachel, there's a 7, yeah. And there's an 11. How many 11s do I need? Just 1. That's the biggest exponent. It's going to be 2 times 3 squared times 7 times 11. Okay, Mr. Dewick, can you do this one in your head? It's going to be 9 times 2, 18. It's going to be 18 times 77. Yuck. Well, 18 times... Sorry? 462? Is it? People shaking their head? It's not 462. 1386? I knew the 400 something was wrong because I was doing the math in my head and I was getting an answer in the thousands. You accidentally did divide by 2? Don't do that. So there is a method for finding the least common multiple, the LCM. Plug back in. So far, so good? Okay, so part of your homework today, Kenzie, I'm going to say find the least common multiple. I want you to notice this 441 right here. What's the exponent on the 3? What's the exponent on the 7? Do you notice how all of the prime factors have a 2 as an exponent? That tells you something. Try taking the square root of 441 on your calculator. What's the square root of 441? Evenly? Oh, are you saying if you do the prime factorization and all of the prime factors are squareds, then your original number was a perfect square? Perfect squares. Perfect squares of whole numbers include 1. What are the perfect squares? 1 times 1 is 1. What's the next perfect square? I'll give you a hint. It's 2 times 2. 4. 9. 16. What's next? 25. What's next? 36. What's next? 49. Then 64. Then 81. Then 100. Then 121. Then 144. You should know those. Next time I hang on to it for a while, kiddo. You guys really suck at looking at your phones. It's pretty obvious to me. You should know the first 12. It helps if you know 13 squared is 169. It helps if you know 14 squared is 196. It helps if you know 15 squared is 225. It helps if you know 16 squared is 256. It helps, but the smaller ones are important. Every perfect square has 2 square roots. 1 positive and 1 negative. What's the square root of 36? Well, 6 times 6 works, but negative 6 times negative 6 also works, because what's a negative times a negative? A positive. Now, when we do this, by the way, what's that the symbol for? That symbol also says, oh, and only give me the positive answer. I know there's 2, but I only want the positive answer. You may not have known that, but that's why when you do it on your calculator, Carl, it only gives you one answer. It doesn't give you both. Okay? By definition, if I say find the square root of something, I want the positive only answer. Yeah, I know there's 2. I want the positive only answer. In fact, we call the positive root the principal root, the main one, the primary one. Okay. It says on the next page, write each of the following as prime factors. All right. 9 is what? I'm going to be really, really clever. Instead of writing 3 and 3, I'm going to say that's a 3 squared. Yes? 36 is now 6 squared isn't prime. I want the primes. Tawny. It's 4 times 9. It's 2 squared. 3 squared. Brendan, can you see a bit of a pattern for perfect squares if you know their prime factorization? Hey, let's keep going. 49 is what? 7 squared. Now, I know 64 is 8 squared, but 8's not prime. 64 is, I'll give you a hint, 2 to the something. Ooh. Does 64 break the pattern? Because I noticed it was squared, 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 squared. 6th? Or can I extend the pattern so it still fits? How can I tell that a number is a perfect square if when I write out the prime factorization, all of the exponents are what? Sarah, louder. You're right. Even. Even. Most common, Rachel, is 2. But if you end up with a to the 4th, I'm telling you, that's a perfect square too. Or if you end up with like a 64 to the 6th, that's a perfect square too. To the 8th, yep. To the 10th, yep. To the 9th, no! So this equals 3 times 3. The square root of 9 is 3. This equals 2 times 2 times 3 times 3. And you can see there's pairs of 2s, another pair, a pair of 3s. 2 times 3 is 6. This is 7 times 7. Square root of 49 is 7. 64 is 1, 2, 3, 4, 5, and we're missing a 2. 6, we're missing a space. It's 6 2s. 1 pair, 2 pairs, 3 pairs. How many pairs are there grand total? 3. The square root of 64 is 2 to the 3rd. By the way, what is 2 to the 3rd when you evaluate it? What is 2 times 2 times 2? Ah. So if you're wondering, hey, before they had calculators, how do they do square roots of really big numbers? Prime factorization, factor tree. Nicole, you want to do me a favor? Nice and hard. Thank you. I'll get the baseball bat. You need the baseball bat? We can do that. I care. I want learning to occur. So we're looking, I think I called this number theory macro. We're looking for patterns. And one of the things we noticed, the prime factorization of perfect squares involves factors which occur in groups of 2. Or as Sarah generalized, you have an even exponent. If they all have even exponents, they must occur in groups of 2. Oh, if you have an odd exponent kicking around, then it's not a perfect square. You don't even need to go to your calculator. You can tell right away, square root won't work. Okay. Psst. If when we were doing square roots, things appeared in pairs, what about the prime factorization of a perfect cube? They'll show up in groups of 3. And that's how you can tell that you can take, and here's your new term of the day, the cube root of something. We're going to introduce you to the cube root. Perfect cubes, 1 times 1 times 1, 1. 2 times 2 times 2. Yep. 3 times 3 times 3, 27. 4 times 4 times 4. Nice. Someone knows his times tables. All right, smart pants. 5 times 5 times 5. Close. $1.25. Six times 6 times 6. It's 216. 7 times 7 times 7. I know it's 300 and I think it's 343 or 349. 343, I think. That 343. That's about where I've stopped memorizing. Well, okay, I do know 10 times 10 times 10 is 1,000. I guess I know that one. I know my 10 times tables. I can do as many of those as you want me to. But I really don't know what 9 cubed is. I know it's in the 800s somewhere, I believe. No, I think it's 729, but don't quote me on that. 8 cubed is, yeah, but that, I would do the math before I wrote down my answer. I wouldn't go from memory on those. You should know the 5 that I've listed here. And I'll even say it's helpful to know 216 is 6 cubed. What's the prime factorization of the following perfect cubes? Well, 27 is 3 to the third. $216. Yeah, is 6 prime? But what's 6 made up of? What times what? 216 is going to be 2 to the third, 3 to the third. Can you see a 6 to the third power kind of hidden in there? I think we're going to have to factor tree for 3,375, though. What goes into 3,375 evenly? 5 times what? Sorry? 5 times what? What am I going to put over? 675? What goes into 670? Oh, let's circle the 5 because it's prime. What goes into 675? 5 times what? 135? What goes into 135? 5 times what? 27. Oh, what's the prime factorization of 27? You know what? I'm going to get really lazy and I'm going to go 3 cubed and I'm just going to end right there. Why not? Oh, can you see the prime factorization? Can I go smaller number than bigger number? And can we always do that? 3 cubed, 5 cubed. Without doing it on your calculator, can you tell me, is 3,375 a perfect cube? Yes, it is. Oh, and this would actually, we can generalize this. You notice for perfect squares, it was anything that was even. Sarah spotted that. For perfect cubes, it's not just a 3, it's anything that 3 goes into. So if I had an exponent that was a 6, it's a perfect cube. Or a 9, that's a perfect cube. Or a 12, that's a perfect cube. Or a 15, that's a perfect cube. Trust me, it is. Now, you do have a cube root button on your calculator. Get your calculators out, please. Get your calculators out, please.